So our next speaker is John Brennan from Cadence Design Systems. John is the Product Management Director for Cadence Design Systems for the past 16 years, focused on verification and recently functional safety. And the title for John's talk is ISO 26262. This changes everything. So over to you, John. And just a reminder, it's a 20-minute talk, please. Thanks, John.
Sure, Mike. Thanks. Hi, everyone. Appreciate the opportunity to come in and speak to you. This presentation, of course, is only 20 minutes, but this is a subset of material that we used at this year's DVCon. So you can get the full version of this by going to the DVCon website. And the specifics here, if I can get my slides to move, here we go. The specifics here are really around, RTL safety integrity, and the main disruptive trends in automotive, and I guess I don't have to tell you guys this, is really around autonomous driving and connectivity. These are the main sort of drivers for semiconductor innovation, and the main concerns actually for safety integrity. At the end of the day, you look at a standard like ISO 26262 and you say, okay, well, how's this going to impact us? Well, it's going to impact us from the perspective of we will now have to be proving the safety integrity of the designs. And from a legal perspective, there is an audit trail now from the system supplier to the subsystem supplier and eventually all the way down to the semiconductor supplier. So all of a sudden, this becomes extremely important. All of a sudden, this becomes an extremely important thing for us to understand and to try to go implement. So obviously, Cadence, our competitors, virtually everyone who's involved in automotive, this becomes a very interesting area, and everyone's investing to try to address the needs of the standard. Now, the standard is an evolving standard. The standard does not address everything. It's not overly definitive. There's a lot of very vague areas, but it fundamentally comes down to three important areas. One is around safety culture and having requirements tracing from system all the way through to component. Be able to prevent problems from arising. Two is being able to actually do measurements. This is sort of metric-driven verification on steroids, right? It's functional verification at all levels of abstraction from the RTL through, as our previous speaker talked about, through software levels. It's safety verification to measure the response of the system to undesirable or unplanned events, and that's where we get the famous stuck at 0, stuck at 1 kinds of measurements that we now need to provide. And the last part is around documentation, which basically proves that the tools do not inject a fault or do not inject a failure into the end work product or the actual design, and that the tools are safe to be used in such a critical, safety-critical kind of applications. And of course, at Cadence, we're addressing all three of these areas, and I want to give you sort of a bit of a highlights in terms of the sort of overall philosophy and implications, but also sort of what the approach is from a hardware development perspective. And when I say hardware, of course, I mean RTL. So the implications for design and verification tools is that if you look at the diagram there on the left-hand side, we need an environment that does requirements traceability where we can combine sort of verification and safety planning, where in the middle we've got this fault-tolerant design, and we're exercising the design not only from the perspective of what we traditionally do with something like a UVM test bench with functional testing, if you will, positive testing, but also now the idea of being able to apply negative testing to that same design to ensure that error scenarios are properly accommodated for. And of course, all this needs to reside in a common database and results database so that it can be traced all the way through. And the whole idea here is to reduce the failure time or fit rate, the probability of an error on a functional side, and I'll contrast this with typical things that people do in test in a little bit, but this is not test. This is functional safety, and functional safety is much, much different than test. But I'll get into that in a little bit. So our approach is to be able to take the same environment and apply positive testing, the functional test, and apply negative testing on the design, and to be able to verify the very specific failure modes, and to be able to statistically test to ensure design integrity. It's going to be impossible to test everything, to test every single node, every single junction, every single transistor in the design. So we have to be, just like in functional verification, we have to be smart about what we decide to go test and why. And so the planning aspect becomes a very, very important part of this overall process. One part of the standard that's not very well defined at all is transient faults. These are single event upsets, single event transients. These are things that they are alluded to, but and most people know that they can be very, very serious types of failure scenarios that have to be accommodated, but again, not very well described or very well articulated in standard as of today. So to make this kind of more real, let's take a look at an example design and tell you how we do this differential analysis. So the very first thing we want to do is we want to verify the correct system behavior of a design, and here we have a kind of sample automotive design down below. We have MCUs that are redundant. We have a lockstep comparator, that's our safety mechanism. We may have a logic system. We may have some ECC, that's our error correction mechanism or a safety mechanism, and there may be some analog in there along with some ECC. So we want to verify the design, very first thing, make sure the design works correctly. And so we use metrics to trace that, to verify that, etc. You guys know the drill there. Then we want to verify the correct system response, functional safety. So use metrics to trace the fault injection to the safety system output. And we want to be able to test enough to ensure the overall confidence of the system. So this is where the statistical part comes into play. We want to measure the outputs of the fault injection. So you can see here on the left-hand side, we can be injecting faults at various areas, and we're going to pick up two fundamental pieces of information. One is the strobe output, which is effectively the functional output. In other words, what is the output of the circuit? What is it supposed to be providing? And then there is a second measurement, which is a safety system output. And this is referred to as a checker output. And this is where we measure the difference actually between these two. And this is where it's really very, very different than DFT. This has given us a differential analysis, whereas DFT is straight injection. So we end up with sort of two strobe points and transient faults, and we exercise that on the safety critical systems. So if we look at a sort of a classification, this is a fault safety classification that we use to try to simplify things a little bit. So on the left-hand side is that functional output, and up top is that checker output. And so we have two scenarios for the checker. It's either undetected or it's detected. And we have two scenarios for the functional output. A fault is either detected or undetected. And the one that really is dangerous is where there is a functional output and a fault is detected, but it is not picked up by the safety circuit and the checker undetects. It does not detect the presence of that fault. So therefore, it cannot take corrective action. All the other cases are safe, some more safe than others, but you can read the descriptions here in the diagram and you can get a sense of sort of what that means. So diagnostic coverage effectively is the bad stuff divided by the good stuff. So we want to know on a percentage basis, you know, how much of the design did we cover, how much of it is stuff that is undetected effectively, where there is a fault but it's undetected, versus all of the other scenarios that are safe. So this is sort of the way that we do differential analysis through the simulator. And the one thing that we've seen is that, sort of the brute force approach, doing forces, for example, trying to do this with assertions, trying to do this with just pure brute force fault injection, it's not going to scale. It doesn't have the ability to be able to handle large-scale designs in any kind of an efficient manner. What is necessary is to be able to apply this greatness of constrained random with ability to do sampling and to be able to have a formal guided kind of approach, because there are some scenarios that will just never happen and we can formally prove that. And there are other scenarios that we want to make sure that we focus on, because that's a critical part of the overall design. So it's really sort of this combination of automation of constrained random with sampling with formal guided that is going to get us the best possible ability to validate and verify the safety integrity of the overall design. So we look at a kind of a typical fault campaign execution. And this is executing a design with a kind of traditional UVM test bench to ensure the safety integrity of that design. But now we've added this new thing called a fault list. And that gets combined together, and the design along with that fault list gets elaborated. We compare effectively a good simulation run from a faulted simulation run, and that's the difference here between the left-hand side and the right-hand side. So after elaboration, we do a good simulation run. We test to ensure the integrity of that. We can reduce the faults set through formal pre-qualification. In other words, we can identify what is actually untestable, and we do that n number of times. In other words, for each fault scenario that we've identified through the planning process, we will generate a simulation, and this is effectively the bad simulation, if you will. This provides us a report of diagnostic coverage, merge that coverage data together, very similar to the way we merge functional coverage today or code coverage today. This all gets merged together. We can apply, again, formal undetectability analysis to some of those outputs, and then we get a final merged report. So you get a sense of sort of what that flow would look like from a simulation and combined formal perspective. Tool confidence level is another big piece of it. TCL is a mandatory part of the ISO 26262. It's covered under Part 8, supporting processes. Customers need to supply what's called a software tool criteria evaluation report for each tool that's used for each design. And I want to make a note that tool confidence and functional confidence are not the same thing. Tool confidence says that is the tool and the ability of the tool to detect errors good enough to develop a safety critical design, and does it not inject a possibility of a failure, a critical failure, into the design itself. It has nothing to do with whether the design works or not. It just has to do with whether or not the tool works or not. So TCL is exclusively a measure of the ability to detect the tool errors. We provide use cases for each of our tools. Each of those use cases has a set of inputs, has a set of outputs, and has a set of error scenarios that are known to us, and therefore are known workarounds or known mechanisms to ensure the integrity of that tool. So we provide the sort of complete TCL documentation that will save our customers time and resources. They take our templates, they modify our templates, and they're, as long as they follow those instructions and add to it maybe any additional things for their own particular use, they're good to go. So this effectively becomes a foundation layer that's necessary for a part of the overall ISO 26262. Oh, okay, good. So I guess in summary here, So functional safety sort of requires new generation of fault injection technology. This is actually more exhaustive. It requires more resources. I didn't get into this part of it, but it is actually more exhaustive than functional verification. We provide the technology to reduce the effort to instrument and execute those fault injection campaigns. The fault injection technology is, you know, this is going to be an emerging area for probably the next 5 years at least. But we've got the starting point of it now with functional safety simulation, with formal technologies, as well as with fault injection campaign executors to simplify the overall job and make it a little bit more automated for you, a little bit more optimized for you, based on existing technologies. So I think with that, I can open up Mike for questions.
Sorry, John. We're just switching microphone.
Okay. Thanks, John, for a very enlightening talk and for finishing on time as well. Thank you. We'll go over to questions now. I think we've got a question online. So there's one question online, John. What role for FMEA in the flow?
So the role of FMEA and what's really referred to as FMEDA, failure modes, effects, and diagnostic analysis. The role of that is to be smarter about how you go about exercising your safety campaign. Not all parts of the circuit are as critical as others, and so you want to apply your safety mechanisms to the critical aspects. FMEDA allows you to do analysis, either top-down analysis or bottom-up analysis of all of your failure scenarios and where to apply your safety circuits, what the probability of those error scenarios might be, and gives you the distribution of those error scenarios across the entire design. That becomes then an input to the overall execution process. So again, that we're smarter about execution versus trying to fault everything in the design.
Okay, thank you. Any questions from Bristol? Cool. There's one question. I'm just going to hand over the mic.
Hi John, Said here. My question is the tool confidence level. Is it something generic that, you know, if it passes the ISO 26262, then the tool can be used with any design and no more work required, or for any particular design, the tool needs to go through the certification again?
Yeah, for every design, there needs to be, because unless the designs are identical, then you can refer to their previous documentation. But effectively, if I get your question correct, for every design, you need to have that booklet. Now, it could be a duplicate, you know, if it's a derivative design or something like that. But it does need to be assembled for each design. If you're a Cadence customer, you go to Cadence Online Support. You'll see all of our documentation there for what's called TCL1 pre-qualification, which is gives you effectively a rubber stamp to TCL1.
John, there's another question online. There's a bit of a follow-up to the FM. I think you described FMEDA in the end. How do you detect errors in functional coverage metrics? I.e., if the tool fails, you're measuring coverage on something that is not.
I'm not sure. Mike, can you repeat that question?
Yeah. I'll do it word for word because I'm not sure I fully understand it either. It's come from Sean Redmond. How do you detect errors in functional coverage metrics? I.e., if the tool fails, then you are measuring coverage on something that is not covered.
So I think I get the question. So this is where we have to differentiate between tool confidence and design confidence. So tool confidence, you do need to go through a process of ensuring the integrity of the tool, and this requires what's called the FMEA process. For each tool, we define a failure mode, and what the impact of that failure mode might be, and what the workaround scenario or validation mechanism is to ensure the integrity of that tool. You have to, at some point, you have to say this is a trusted tool. You have to say this tool is designed to be with our qualifications in place and with our processes in place is safe operation. So if you trust the tool, then you therefore trust the ability to use the tool in a safety critical design. So I guess that's probably my best answer that I can provide.
I think it's a good answer as well. Thanks, John. I understood your answer. And the last question is a follow-up to the original FM EDA from Sam Baskell. Any plans to offer FM EDA tool?
This is an area we're constantly evaluating, and right now it's not a very mature area. We expect it to be so in the coming years. So I guess stay tuned. No current plans.
Okay, we have one final question from Bristol, so make this our last question so we can move on. Do you want to introduce yourself?
Yeah, my name's Paul from Imagination. A quick question on the tools. The tools are always being upgraded and developed, so if you rubber stamp with a tool for a given product, do you have to then preserve the ability to reproduce that tool over a lifetime of a product, or do you have to update your certification every time you update the tool?
Yeah, we just signed ourselves up for re-updating because, as you know, in order to give you the additional productivity that you require, we have to keep updating the tools. So we will be updating our documentation accordingly. And of course, you can use the older tools and the older documentation, but we feel now obligated that we have to keep the tool documentation updated as well too. So there'll be another version next year, for example.
Okay, I think we're finished there, John. I think it was a very good talk, and I think as demonstrated by a number of questions you got. So thank you very much to John, and we'll move on. Thank you.
You're welcome.